Welcome to the On My Workbench channel. Back in February of 2022, I posted a video on how I solved the communication issue with the EG4LL batteries. I did it by building a 4-way parallel RS-485 cable connected to the RS-485 ports on the front panel of the batteries. The 4-way parallel cable used an RS-485 to USB adapter plugged into a USB port on a Windows computer running the BMS software. A link to the video will be in the description. After I got the BMS software to work with all 4 of my batteries, I wanted a system where I could not only view the battery data, but the data from my solar panels, my charge controller, and my inverter, all from one location, and I wanted to do it over my local area network. While that may sound like a fairly simple task, the issue that I had was that my charge controller is an Outback FLEXmax 80, my batteries are the EG4LL Lithium Iron Phosphate, and my inverter is a Schneider Electric SW and the solar panels are dumb devices without any data feedback other than voltage and current. As it turned out, all of my solar devices use very different communication protocols or no communication protocol at all, as with the solar panels. The FLEXmax 80 charge controllers have a built-in RJ45 data port, but its output data was much more complicated than what I wanted to tackle with this project, as it was going to be my first project utilizing a Raspberry Pi, the Python programming language, the Flask web framework, and the HTML web page markup language. The EG4LL batteries use a fairly straightforward form of the Modbus communications protocol in a request and reply system to retrieve the data from the batteries. The Schneider Electric SW inverter uses Modbus similar to that of the EG4LL batteries, but it too was slightly different. To view the data from each of the devices, you had to be at the device. As for the solar panels being dumb devices, you needed to read the voltage and current of the solar panels from the charge controller display screens. And for the charge controller, you had to view its data from the same display screens, and the charge controller has its data spread across multiple screens that you would have to scroll through. The FLEXmax 80 has the option of using a remotely located display screen called the Outback Mate. The Outback Mate utilizes the RJ45 port that's built into the FLEXmax 80 to communicate with it. While it is possible to remotely locate the Outback Mate, it would require the use of a long Ethernet cable running from the charge controller to the Outback Mate display unit. The Outback Mate has an RS-232 port built into it that can be connected to a computer running some flavor of RS-232 monitoring software to read and display its data. Another option would have been to co-locate the Outback Mate with the FLEXmax 80 charge controller and run a long RS-232 cable from the Outback Mate to a remotely located computer to display its data. The data from the EG4LL batteries can be viewed by using the LCD display panels on the front of the batteries, or by using the BMS software, which would require the use of a computer located at the batteries, or by having a long RS-485 cable running from the location of the batteries to the location of the computer. The last device is my Schneider Electric SW inverter. I have the option of viewing its data from a display screen located with the inverter, and it's the only device that utilizes my local area network to display its data. Its data can be viewed from any internet-capable device, such as a phone, tablet, or computer, using a web browser over my local area network. I looked at 2 software options such as Node-RED and Grafana from Grafana Labs, but I did not like either one. Links will be in the description. I opted to go with a Raspberry Pi 3 Model B+, Python programming language, Flask web framework, and HTML web page markup language, all of which I knew nothing about. Links will be in the description. I started reading up on the Internet of Things and how to control devices over a local area network from a web browser. I learned about front-end web servers versus back-end web servers. I started outlining what I wanted the system to look like and what I wanted it to do. I drew up a block diagram with written description of how I thought the control and data flow should work. I found an article from May 19, 2021 called Controlling GPIO Pins of a Raspberry Pi with a Web Page. This article was on controlling the GPIO pins, the general purpose input-output pins on a Raspberry Pi from a web browser. A link will be in the description. It was a very poorly written article and hard to follow and very confusing for a newbie. After a lot of trial and error, I finally got the code in the article to work. I used the 4-way parallel RS-485 cable and the 4-way splitter box that I showed in other videos to figure out how the BMS software sends requests for data to the batteries and how that data is returned back to the BMS software. I used the 4-way splitter box to connect computer number 1 running the BMS software to the batteries. The splitter box allowed me to sample the data that was going from the BMS software to the batteries on a second computer and to monitor the data that the battery sent back to the BMS software. I used a software program called XCTU from Digi International. XCTU was originally used for the programming and testing of spread spectrum radio modems that Digi International produces. To keep things simple, I only used battery number 2 for the following tests. The XCTU software allowed me to see the data that was sent by the BMS software to battery number 2, and to see the data that battery number 2 sent back to the BMS software. This allowed me to see what was going on between the BMS software and battery number 2. And that's when I noticed that the BMS software sends out a 16-bit string of data to each of the batteries, and each of the strings are addressed to a respective battery. In my case, I have 4 of the EG4LL batteries, and they are addressed 02, 03, 04, and 05. But I only use battery 02 for this test. So the 16 bytes of data that is sent to battery number 2 looks like this. The first 2 bytes are the battery's address. The next 12 bytes tells the battery what data the BMS software wants. The 02 is the battery's address. The 03 is a function code. 03 tells the battery that it is receiving a read-only request. The first set of zeros is the minus offset, so 00 means that there is no offset. The second set of zeros is the number of the first address register to receive data from, so the first address register is 00. The 27 is the number of address registers to get data from, and the 05 E3 are the CRC checksum. If you look at the data request string for battery number 2, 02, 03, 00, 00, 00, 27, 05, E3, and the data request string for battery number 3, 03, 03, 00, 00, 00, 27, 04, 32. You can clearly see that the only differences are the battery ID address bytes and the checksum bytes. The rest of the 2 strings are the same. The battery then sends its reply back to the computer running the BMS software over the RS-485 cable. This is a sample of the return string of data for battery number 2. This is repeated for the remaining 3 batteries, and the entire process is repeated over and over again as long as the BMS software is running. On occasion, the BMS software will send out a different 16 bytes to the batteries that look like this. When compared to the request for the battery data, the difference can be seen in the makeup of the 2 strings. Where the battery data request string looks like this new string looks like this. The first 2 bytes in the new string is the address for the battery. The difference in these strings, as I have been able to determine, is that the new strings are a request for a serial number for each of the batteries. I used the data from both BMS software's main BMS monitoring screen and the data from the BMS software's communication screen by doing a screen grab on the BMS monitoring screen and saving it as an image, and by copying and pasting the data collected from the BMS software's communication screen and saving it as a text file. I could then compare the data from the 2 screens. I used the calculator in Windows in the programmer mode with the calculator set for decimal input. I converted the decimal voltage value of 53.45, the voltage that was displayed in the BMS monitoring screen, from decimal to hex so I could find it in the data string from battery number 2. It was 14E1 hex. Then I found where it was located in the string, and I repeated this for all the other data fields that are displayed on the BMS monitoring screen. The easiest way to do this was to configure the BMS software to collect data only from battery number 2 and let it collect data for 20 to 30 seconds, and confirm that the communications screen is showing data only from battery number 2. Then go back to the BMS monitoring screen and click the Stop Monitoring button in the Monitor Status box under the pack ID. This will stop the BMS software from collecting any more data. Then click on the Communications tab and use Ctrl+A to select data, and use Ctrl+C to copy the data, then paste it into a text file such as Notepad and save the file. This data has to be collected during the same time frame, so the data from the BMS software's main BMS monitoring screen and the data from the BMS software's communication screen will match. As you look at the 16-byte outgoing string, remember any string starting with 02 and ending with checksum of 05E3 is a request for data intended for battery number 2, and any string with 02 and ending with a checksum of D5EB is a request for serial number data and is intended for battery number 2. The strings for the other batteries will have different address and checksums. Also, the strings from the batteries with the battery data will have 168 bytes, and the serial number strings will only have 101 bytes. Once I knew the relationship between the battery voltage displayed on the BMS monitoring screen and its location as a hex value in the return data string of battery number 2, I could then determine the relationship for the rest of the battery information displayed on the BMS monitoring screen. To get the state of charge and amp hours remaining, I had to disconnect the solar panels from the charge controller and disconnect the inverter from its grid input power, and to put a load on the inverter so the batteries would run down enough so the state of charge and amp hours remaining would show values less than 100%. As for the location for the state of health, I need more information, and as for the capacity, I believe the 100 amp hour is a fixed value for 48 volt EG4LL batteries. I believe that it would be displayed as 200 amps on a 24 volt EG4LL battery and 400 on the 12 volt battery. If anyone has a 12 or 24 volt EG4LL battery that could check it, please let me know. The next thing that I needed to do was to see if I could send the data request string to battery number 2 and get the correct data reply back from battery number 2. So I used the packet send function that's built into XCTU. It worked. I used the XCTU software to send the data request strings to battery 2 and got the correct data back from battery 2. Next, I tested it with my remaining 3 batteries, and they worked the same as battery 2. So now I could send the data request strings to the batteries and receive the data back from the batteries. The next thing that I needed to do was to see if I could send a request for the battery serial number to battery number 2 and get the serial number data back from battery number 2. I did, and it worked. And it worked for the remaining 3 batteries as well. Next, I wanted to see if I could send the request data to battery number 2 and receive the data back from battery number 2 using an RS-485 to USB adapter on one of the Raspberry Pi's USB ports. So I started researching how to send data to a Raspberry Pi USB port and how to receive data back from a USB port. With the help of my longtime friend Robert, we came up with a code to do just that. We sent the request data string to battery number 2 from the Raspberry Pi, and we could view the reply back from the battery number 2 on the Python shell display. So now I could send a request for data string to battery number 2, and I could receive the correct data back from battery number 2. So now I could request data from all 4 batteries and read the data back from the batteries and display it on the Python shell terminal screen. Next, I want to display that information on a web page. Please check back for part 2 of my project SolarCop, where I explain how I read and display the data from the Outback FLEXmax 80 charge controller by using the Outback Mate RS-232 interface. Please Please check back with the On My Workbench channel for more videos on cool stuff. Please subscribe, like, comment, share, and click the little bell. And thanks for watching the On My Workbench channel.